Please subscribe to support the channel. Despite all our dreams of conquering the stars, the truth is both humbling and haunting. We may never truly leave Earth. For generations, humanity has imagined escaping our blue planet, building civilizations among the stars, and finding new worlds to call home. But behind that dream lies an uncomfortable reality. The universe is vast, hostile, and utterly indifferent to our survival. Every force of nature, distance, radiation, gravity, and time conspires to keep us bound to the only world that sustains us. Earth isn't just where we live, it's where we belong. And as much as we look up and dream, we may have to accept that our destiny was never to leave, but to understand and protect the miracle we already have. For all our brilliance, for all the centuries of progress that have brought us from stone tools to supercomputers, humanity still faces a barrier that feels almost mocking in its simplicity: speed. We can reach orbit, we can send probes across the solar system, we've even touched the edges of interstellar space with the Voyager spacecrafts. But when it comes to actually traveling beyond our celestial neighborhood, truly venturing into the cosmic ocean, our technology slows to a crawl. Our rockets, for all their fiery spectacle, are still primitive in the grand scale of the universe. They are, in essence, controlled explosions strapped to fragile metal shells. The chemical propulsion systems we rely on today operate on the same fundamental principles as those designed in the mid-20th century. Sure, they're safer, more efficient, and more precisely engineered, but in terms of cosmic reach, they are almost laughably limited. Even the most powerful rocket ever built, NASA's Space Launch System or SpaceX's Starship, can barely nudge us past the moon. Mars, our nearest planetary neighbor, takes months to reach under the most favorable conditions. And that's still within the comforting cradle of our solar system. When we talk about leaving Earth for real, when we talk about interstellar travel, the scale of the problem becomes almost incomprehensible. The nearest star system, Alpha Centauri, is over 4 light-years away. That's nearly 40 trillion kilometers. To put that in perspective, if Earth and the Moon were 1 centimeter apart, Alpha Centauri would be over 300 kilometers away on that same scale. Now imagine crossing that distance using our current propulsion technology. The fastest human-made object ever built, NASA's Parker Solar Probe, travels at about 700,000 kilometers per hour, roughly 0.064% the speed of light. At that speed, it would take over 6,600 years just to reach Alpha Centauri. Thousands of generations would live and die aboard a ship that never even makes it to its destination. That's not interstellar travel, that's a slow drift into oblivion. People often say, well, we'll just invent faster ships. But the reality is much harsher. Physics itself stands in our way. Every time we try to accelerate mass to a higher speed, the energy required increases exponentially. To reach even a fraction of light speed, we'd need an amount of fuel and energy so immense it defies practicality. The rocket equation, that merciless bit of mathematics, makes sure of it. For every kilogram of payload, you need exponentially more fuel, and then more fuel to carry that fuel, and so on. The result? A ship so massive and inefficient that it collapses under its own design. Science fiction often waves this problem away with a single line of dialogue: engage warp drive or activate hyperspace engines. But in the real universe, there is no such magic. Concepts like nuclear propulsion, antimatter drives, or solar sails offer fascinating possibilities, but they are either theoretical, inherently unstable, or technologically unfeasible at scale. Even if we somehow perfected them, the limits of energy conversion, cosmic hazards, and material endurance would still make practical interstellar travel nearly impossible. And yet our desire persists. We build telescopes that can peer billions of light years away, but we can barely leave the orbit of our own planet with enormous effort. The irony cuts deep. We can see the stars more clearly than ever before, but we are trapped by the physics that govern them. It's as if the universe allows us to look, but not to touch. When we dream of colonizing Mars, we imagine fleets of ships moving effortlessly through the void. But every mission to the Red Planet pushes our technology to its absolute limits. The delays in communication, the precise fuel calculations, the thin margins of error, all of it reveal how fragile our progress really is. Even the International Space Station, orbiting just a few hundred kilometers above us, requires constant maintenance, resupply missions, and problem-solving ingenuity to keep a handful of people alive. The deeper we go, the clearer it becomes that space travel is not just a question of innovation, it's a confrontation with reality itself. The cold vacuum doesn't care about ambition. The laws of motion and energy are absolute. Every kilogram of mass, every joule of power, every spark of thrust, they all obey the same unyielding cosmic rules. This isn't to say that humanity lacks imagination or courage. We've sent robots to the edge of the solar system, landed on comets, and mapped worlds we once thought unreachable. But when you step back and see the scale of it, when you compare our tiny technological leaps to the unimaginable distances before us, you begin to understand how truly trapped we are by physics. And this technological cage doesn't just limit our movement, it defines our future. Because if we can't move beyond our solar system with anything approaching reasonable timescales, then the dream of a second Earth is not just improbable, but irrelevant. We are, at least for now, a species confined to one fragile planet. Yet, there's something poetic in that confinement. Our limits remind us of how extraordinary it is that we've even made it this far, that we can reach orbit, land on the moon, and dream of Mars. But those same limits also whisper a truth that's hard to face. The stars may never be ours to claim. They may forever remain what they've always been, distant lights that guide our imagination but resist our touch.
Still, our technological struggle is only part of the story. Because even if we could somehow build faster ships, there's another barrier. One that doesn't lie in equations or engines, but in the scale of existence itself. The vastness of space is not merely large. It is unimaginable. A void so deep that distance itself begins to lose meaning. And that's where the next truth begins to unfold. A truth not about machines or rockets, but about the incomprehensible vastness of the cosmos and how even our most ambitious technology is rendered meaningless by the sheer scale of the universe around us. When we talk about space, we often use words like vast, infinite, or endless, but even those words fail to capture what the universe truly is. The human mind is not built to understand such scales. We measure our lives in years, our journeys in miles, our days by the rising and setting of a single sun. But space stretches beyond all of that. It dwarfs our imagination. It mocks our sense of distance. It is so incomprehensibly large that even light, the fastest thing in existence, takes ages to traverse it. The nearest star system, Alpha Centauri, sits over 4 light-years away. That means the light leaving that star tonight won't reach us until 4 years from now. If we somehow managed to travel at the speed of the fastest human-made object, it would still take tens of thousands of years to get there. And that's just the next door over. We tend to picture space like an ocean, with planets and stars as islands scattered across its surface, but that image is wrong. Space isn't dotted with islands close enough to sail between. It's a void, a black sea so empty and vast that even the most optimistic dreams of exploration crumble before it. Between our solar system and the next lies not a few million kilometers, but trillions upon trillions. You could line up every planet in our solar system end to end, and you wouldn't even begin to bridge the distance to the next star. It's strange. We look up and see the night sky filled with stars and it feels crowded. It looks as if the universe is teeming with light, as if every point in the sky could be reached with a big enough rocket. But what we're really seeing is an illusion of closeness. Those stars are impossibly far apart. They're light traveling for hundreds, thousands, even millions of years before reaching us. When you gaze at the night sky, you are not looking at now. You're looking at the past, at ghosts of stars that might already be dead, their light still crossing the endless gulf toward us. Even within our own cosmic backyard, the scale is absurd. The distance from Earth to the Sun is about 150 million kilometers, a number we can barely imagine. Yet, the nearest planet Mars can be 400 million kilometers depending on the orbit. And beyond Neptune, our solar system stretches into a vast, frozen wilderness, the Kuiper Belt and the Oort cloud, extending for billions of kilometers until the Sun's influence finally fades into true interstellar space. Voyager 1, the most distant human-made object, has been traveling for over 45 years, moving faster than any spacecraft before it, and it hasn't even reached another star. It hasn't even come close. If we could somehow stand outside the Milky Way and look back at it, we'd see a glowing spiral of hundreds of billions of stars, a magnificent whirlpool of light spanning 100,000 light-years across. 100,000 light-years. That means that even if you could travel at the speed of light, something no physical object can do, it would still take you 100,000 years just to cross our own galaxy. And beyond the Milky Way, there are hundreds of billions of other galaxies, each filled with its own suns, planets, and mysteries. The universe doesn't just feel infinite, it behaves as if it is. When you try to imagine those numbers, they stop meaning anything. Our language breaks down. You can say trillions of kilometers or billions of light years, but the human mind cannot visualize that. We can barely grasp the distance from one continent to another, let alone the space between galaxies. The cosmos is not built for beings like us to traverse. It is a realm of incomprehensible scale, where even the fastest thing in existence crawls compared to the immensity it must cross. And in that realization lies a strange kind of humility. For all our pride, for all our dreams of expansion and conquest, we are creatures confined to a single speck in an ocean so vast, it defies reason. Our entire solar system, every planet, every moon we've ever launched, could disappear into the dark, and the universe would not notice. We would not leave a mark. The distances between the stars make even communication difficult. A message traveling at the speed of light would take years, decades, or centuries to reach its destination, and by then, those who sent it would be long gone. It's not that the universe is trying to keep us out, it's just that it doesn't care. The distances are not obstacles placed by design. They are the natural result of cosmic expansion, of physics, of the way reality itself is structured. Space is not built for connection. It is built for silence. And that silence, that emptiness, is what makes Earth feel even more miraculous. Because against the backdrop of that infinite void, here we are, on a world where distance feels small, where life connects across oceans, where we can breathe, move, and speak without delay. Earth feels tiny compared to the universe, yet it's the only place where the distances between living things mean anything at all.
But even if we could find a way to cross those distances, to endure the endless dark between the stars, there's another barrier waiting for us. One not of physics, but of biology. Because even if we could build a ship that could fly forever, our bodies may not survive the journey. We are built for Earth's air, its gravity, its rhythm of day and night. Take that away, and what's left is a fragile organism adrift in an environment that doesn't care if it lives or dies. Our bodies, for all their complexity and resilience, are astonishingly delicate when removed from the conditions of Earth. Every organ, every cell, every heartbeat has evolved over millions of years in a very specific environment. One defined by gravity, atmospheric pressure, oxygen, and the magnetic shield of our planet. Step beyond those boundaries, and our biological systems, which perform flawlessly here, begin to falter. In microgravity, bones lose density at alarming rates.
Muscles atrophy even with rigorous exercise, and the cardiovascular system struggles to adapt to the absence of weight. Astronauts returning from long-duration missions often walk with difficulty, their once powerful muscles unable to hold their own body weight, their bones fragile as if they had aged decades in mere months. Our senses, too, are calibrated to Earth. Vision adjusts to constant gravity and familiar landscapes. Balance is maintained by the inner ear's perception of up and down, a perception that unravels completely in the weightless void. Even the sense of taste changes in space, as fluids shift and blunt the tongue's sensitivity. The human body, remarkable as it is, has become intricately bound to a planet we barely appreciate until it is stripped away. Then there's the simple yet brutal reality of exposure. Earth shields us from the harshness of the cosmos in ways we almost never notice. The atmosphere filters out deadly radiation, moderates temperature swings, and provides the exact composition of gases necessary for our metabolism. Remove these protections and survival becomes a constant struggle. A single breach in a spacecraft's hull or a momentary failure of life support systems could be fatal. Even small doses of cosmic radiation, imperceptible yet relentless, begin to damage DNA, accelerate aging, and increase the risk of cancer. Every layer of protection we take for granted on the surface is a fragile gift of our home planet, one that must be artificially recreated in the void. Beyond the physical, there is the fragility of our biology at the molecular level. Immune function and cell regeneration are all tuned to Earth's conditions. Remove gravity or expose the body to radiation for extended periods, and these systems falter. Cells mutate, hormones misfire, and the subtle biochemical symphony that sustains life starts to break down. We may survive short visits, but long-term habitation of space or another planet remains an experiment with ourselves as the test subjects. An experiment where failure can come slowly, invisibly, and irrevocably. Even our resilience to stress is conditional. On Earth, we cope with challenges because our bodies and minds evolved in synchrony with the environment. In space, the constant need for vigilance against equipment failure, radiation, and resource scarcity compounds every physical weakness. Simple tasks like walking, lifting, or even eating become monumental efforts. Our bodies, so adaptive within the confines of Earth, become liabilities when those confines disappear. This fragility is a stark reminder of how intricately tied we are to the planet we call home. Earth is not just a backdrop for our lives, it is the medium that allows life to exist at all. Gravity, oxygen, magnetic fields, and atmospheric protection are not conveniences, they are fundamental requirements for survival. Remove any one of them, and the human body, marvelous as it is, begins to unravel. The irony is that the very dreams that drive us toward the stars also confront us with our limitations. We envision bold voyages and interstellar colonies, yet our bodies whisper a constant caution. We are not designed for the void. Every system in us is a testament to Earth's singularity. Every bone, every cell, every heartbeat has evolved over millions of years in a very specific environment, one defined by gravity, oxygen, and magnetic shield of our planet. This fragility isn't just about surviving in space, it's about thriving. Even if we could shield ourselves from radiation and artificial gravity, the wear and tear on our bodies would make long-term existence outside Earth a precarious gamble. Human life is tethered not just to a physical location, but to a network of conditions that are nearly impossible to replicate elsewhere. Every protective system we build is a patchwork solution, a temporary mimicry of what Earth provides naturally. In leaving Earth, we leave more than soil and water behind. We leave the environment that allowed life to sculpt us into the beings we are. We step into a universe that is fundamentally hostile, and in doing so, confront the extraordinary delicacy of our own existence. Space is not merely a frontier, it is a mirror, reflecting the limits of our biology and revealing just how deeply, irrevocably, we are Earth-bound.
Beyond the tangible challenges of gravity and the fragility of our bodies lies a far more insidious threat: cosmic radiation. It is invisible, silent, and relentless. On Earth, we live under the protective embrace of our planet's magnetic field and thick atmosphere, both of which act as shields against high-energy particles from the Sun and the depths of the galaxy. Without these shields, however, space becomes a storm of deadly radiation, bombarding every cell in our body with energies that our biology never evolved to withstand. Even a brief exposure can alter DNA, and prolonged exposure slowly accumulates damage, increasing the risk of cancer, degenerative diseases, and potentially irreversible cellular breakdown. Radiation in space is not a single hazard, but a complex tapestry of threats. Solar particle events, eruptions from our own sun, can release clouds of charged particles traveling at near light speed. Cosmic rays, originating from distant supernova and other cataclysmic cosmic events, streak through space with energies far beyond what our cells can tolerate. Unlike ultraviolet radiation, which is mostly blocked by the ozone layer, these particles penetrate deeply, slicing through tissue, altering molecules, and initiating chains of cellular destruction invisible to the naked eye. One moment, an astronaut might be safely conducting a spacewalk. The next, they are being pierced by a rain of high-energy particles that slowly rewrite their biological blueprint. The damage is cumulative. Each particle that passes through the body can break DNA strands or create free radicals, chemically reactive molecules that disrupt cellular function. Over weeks, months, and years, these seemingly minor insults add up, increasing the likelihood of mutations, cancer, and organ degeneration. On Earth, our biology is adapted to repair such damage efficiently. In space, however, the rate of damage exceeds our ability to heal. What may take decades to manifest as disease on Earth can accelerate in space, turning a few years of exposure into a potential death sentence. Even spacecraft and protective suits, as advanced as they are, provide only limited defense. Thick layers of metal can shield some radiation, but they add weight and cannot block all particles, especially the highly energetic cosmic rays that pierce almost any barrier. Some proposed solutions, like water shielding or magnetic fields around spacecraft, are theoretically promising, but remain largely experimental and impractical for long-duration missions. In other words, radiation in deep space cannot be escaped. It can only be mitigated, and mitigation is never perfect. The Moon and Mars, often touted as stepping stones for humanity, offer little relief. Mars has a thin atmosphere and no global magnetic field. Its surface is bombarded constantly with radiation levels hundreds of times higher than those on Earth. Astronauts attempting to colonize Mars would have to spend nearly all of their time inside heavily shielded habitats, and even then, prolonged exposure would take a toll on their bodies. A human being born and raised on Mars would face a lifetime of invisible assault on their cells, a risk entirely absent for those who remain on Earth. Radiation is also a silent psychological burden. Unlike the immediate danger of a collapsing spacecraft or a micrometeorite strike, radiation works slowly, invisibly, and indiscriminately. You cannot see it, feel it, or hear it, yet its effects are just as real and just as deadly. It is a constant, inescapable reminder of how alien and hostile space truly is. For every step beyond Earth, there is an invisible storm that no amount of courage or determination can fully avoid. This threat compounds all the other limitations we face. Even if we could solve propulsion, survive microgravity, and maintain supplies of air and water, the radiation of deep space would remain an unyielding adversary. Every cell in our body, every strand of DNA is under constant assault, a reminder that we are built for Earth and only Earth. Leave its magnetic shield and atmosphere, and we expose ourselves to the raw, unforgiving energy of the cosmos. It is a sobering truth. Our dreams of exploration and colonization brush up against forces that our biology cannot overcome. Radiation is not an obstacle that can be engineered away or ignored.
It is a fundamental property of space, as intrinsic to the cosmos as gravity or distance, and it enforces a limit on how far we can venture without facing severe, potentially fatal consequences. The irony is cruel. We look to the stars as symbols of freedom, as destinations of adventure and promise. Yet those same stars sent invisible daggers towards us, challenging every instinct to explore. For all our innovation, all our ingenuity, the universe enforces its rules silently but absolutely. Earth is our shield. Our planet's magnetic field and atmosphere are not mere conveniences, they are the guardians of our very existence. Step beyond them, and we enter a world where life as we know it struggles to endure. In the cold vastness beyond our planet, radiation is the ultimate reminder of human fragility. It underscores a simple but devastating fact. The cosmos is not a welcoming place. It is indifferent, relentless, and profoundly hostile. And the longer we dream of leaving Earth, the more we confront the truth that without its protection, our bodies, so perfectly honed for this one world, may simply not survive the journey. Beyond the physical dangers of microgravity, fragility, and cosmic radiation lies another, less visible threat: the human mind itself. Space is not just an inhospitable environment for the body, it's a crucible for psychology. Humans are social, tactile, and sensory creatures, deeply tied to the rhythms and familiarities of life on Earth. The vast emptiness of space strips away those anchors. For those on long-term missions, whether in orbit, on the moon, or eventually on Mars, isolation is relentless. There is no natural day-night cycle beyond artificial lighting, no fresh breeze, no sound of wind or rustling leaves, no distant ocean waves. Instead, there's a sterile environment of metal walls, recycled air, and a vacuum beyond the hull. The mind, deprived of its habitual cues and sensory comforts, begins to fray.
Loneliness becomes more than a feeling. It is a physiological stressor. Even in small crews, tension can mount as personalities clash under continuous confinement. Privacy is nearly non-existent, and communication with Earth is delayed or limited. On missions beyond the moon, messages from home can take minutes or even hours to reach a crew, a subtle but constant reminder that they are profoundly disconnected from the world they grew up in. Over time, this psychological distance deepens. Familiar voices, human touch, and social nuance, all essential to mental well-being, become luxuries that cannot be fully replaced. Confinement compounds the problem. Humans evolved for movement, exploration, and the ability to change surroundings. In space, corridors are narrow, rooms are tiny, and horizons are artificial. Days blur into weeks and months with little variation in environment or activity. Even for highly trained astronauts, prolonged confinement can lead to mood swings, irritability, and depression. The same monotonous routines meant to maintain life support and mission objectives can paradoxically accelerate cognitive and emotional strain. Sleep cycles often collapse, circadian rhythms falter under artificial light, and subtle but cumulative stress begins to impair judgment, memory, and coordination. Beyond these mental health challenges, there is an existential dimension to isolation in space. Astronauts often describe a sense of disconnection from Earth itself, a feeling of being suspended in a void where the familiar markers of life, mountains, rivers, forests, cities, are gone. Even when looking out at the stars, the beauty of space can feel paradoxically alienating, awe-inspiring yet utterly indifferent to the human experience. Extended separation from Earth and its communities creates a subtle psychological erosion, a slow questioning of meaning and purpose in an environment designed only for survival, not for the flourishing of human consciousness. Communication limitations exacerbate the sense of isolation. Beyond Mars, even a simple conversation with someone on Earth can take up to 20 minutes to transmit one way, making real-time interaction impossible. That delay disrupts not only social bonding, but also the capacity to seek immediate comfort, advice, or reassurance from loved ones. Over months and years, this creates a feedback loop of detachment,
where crew members are forced to rely entirely on themselves and each other in an environment that feels increasingly alien and threatening. Research from long-duration missions on the International Space Station provide insight into these challenges, but even they are limited. The ISS orbits Earth every 90 minutes, providing frequent visual contact with our planet. Crews experience real-time communication and a sense of proximity that would be impossible on deep space missions. Yet, astronauts report issues with mood, motivation, sleep, and even cognitive performance despite these advantages. Extrapolate that to interplanetary or interstellar travel, and the mental burden becomes staggering. Isolation also amplifies fear and the perception of risk. Every minor malfunction, a crack in the hull, a flicker of instrumentation, a delay in life support systems, becomes psychologically magnified. The mind constantly calculates threats in an environment where any error can be fatal, and stress responses are amplified. The long-term effect is a continuous low-level anxiety that chips away at morale, focus, and decision-making capacity. Human beings are social creatures, wired for connection, sensory richness, and environmental variability. Space deprives us of all three. While technology can simulate communication, entertainment, or even artificial scenery, these are pale substitutes for the dynamic, interactive world we evolved to inhabit. Over time, the mind begins to crave the earthly constants that sustain it: gravity, weather, forests, oceans, and even the chaotic unpredictability of daily life. Without these, psychological strain accumulates in ways that no amount of engineering can fully prevent. Ultimately, the mental hazards of space reveal a profound truth. Survival in the cosmos is not merely a matter of engineering better spacecraft or shielding bodies from radiation. It is a matter of sustaining the human psyche, a challenge far more delicate and less predictable than any rocket launch. The mind cannot flourish in sterile metal corridors, recycled air, or under artificial lights, no matter how meticulously designed. Long-term space travel imposes not just physical limits, but existential ones, confronting every astronaut with the quiet, crushing weight of isolation and the alien indifference of the universe. Even if we could somehow solve the challenges of gravity, radiation, and psychological strain, another harsh reality remains. We are entirely dependent on Earth for survival. Every breath we take, every drop of water we drink, every calorie of food we consume originates from the delicate, self-sustaining ecosystem of our planet. Earth is not merely a backdrop for life, it is the very machinery that makes life possible. Our atmosphere provides oxygen in a precise balance with nitrogen and trace gases. Our hydrologic cycle delivers fresh water, and the soil beneath our feet cycles nutrients in ways no artificial system has yet replicated. Remove us from this network, and survival becomes an engineering problem of staggering complexity. Consider air. On Earth, it seems ubiquitous, effortless. We inhale without thought, and the planet replenishes oxygen constantly through forests, oceans, and microbial life. In space, that simple convenience evaporates. Every molecule must be recycled, purified, or carried along for the journey. Space stations rely on sophisticated life support systems to scrub carbon dioxide, maintain pressure, and regulate oxygen levels. A single failure can be catastrophic. Even with the best technology, these systems are far from foolproof, and the margin for error is razor thin. On Mars or the Moon, where no breathable atmosphere exists, humans would need entirely closed-loop systems, constantly monitored and maintained. One malfunction could leave a crew suffocating or trapped in a life-threatening imbalance. Water is equally essential and equally fragile. While some water can be recycled aboard spacecraft, the process is complex, energy-intensive, and never fully efficient. Contamination, leaks, or equipment breakdowns can quickly escalate into life-threatening crises. On Earth, we take water for granted because our planet naturally recycles it through rainfall, rivers, and aquifers. Attempting to replicate that process artificially in a completely controlled environment is daunting. A closed habitat can't easily adapt to unforeseen demands, contamination events, or mechanical failures, vulnerabilities that do not exist for life on Earth.
Then there's food, the most difficult resource to replace in any meaningful way. Earth's agricultural systems operate through a delicate balance of soil, water, sunlight, and biology. Photosynthesis, pollination, nutrient cycles all evolved over billions of years and continue largely without human intervention. To replicate even a fraction of that system in space, we must engineer artificial soil, hydroponic or aeroponic systems, and lighting that mimics the sun, while managing nutrient balances and microbial populations. Growth cycles take weeks or months, leaving little room for error. Crop failures, contamination, or unforeseen environmental fluctuations could devastate an entire mission. Moreover, the caloric and nutritional demands of humans are high. Sustaining a population on another world would require enormous infrastructure just to feed them, far beyond what any mission to date has attempted. Beyond individual resources, there is the matter of ecological interdependence. Life on Earth is not just a collection of separate necessities, it is a network. Plants produce oxygen and recycle carbon, microbes maintain soil fertility, insects pollinate crops, and countless other organisms contribute to an intricate balance. Reproducing that network artificially is orders of magnitude more complicated than simply storing supplies in tanks or boxes. Even slight deviations can cascade into catastrophic failures. We may succeed in creating small-scale biomes or experimental ecosystems, but sustaining human life indefinitely in isolation from Earth is something we have yet to achieve, and the challenges grow exponentially as time and population increase. This dependency underscores a harsh truth. We cannot simply take Earth with us in a spaceship. Every resource we rely on must either be carried, recycled, or artificially recreated, and all three options are limited by technology, energy, and space. The further we travel, the harder it becomes to maintain these life-supporting systems. On Mars or beyond, resupply missions would be costly, infrequent, and vulnerable to delays or failure. Even the smallest miscalculation, a broken filter, a spoiled crop, or a leak in the water system, could escalate into a survival crisis in a matter of hours or days. The problem extends to long-term habitation. Reproducing an entire ecosystem outside of Earth's complex, interdependent system is nearly impossible. Every organism, every microorganism, and every chemical cycle interacts in ways we barely understand. Attempting to build a sustainable environment from scratch is not just technically difficult, it is a race against the unpredictable variables of biology, chemistry, and physics. Unlike Earth, where life evolved to sustain itself, every human-made ecosystem is fragile, brittle, and dependent on continuous intervention. Even in science fiction, this dependency is often glossed over. Stories of terraformed planets, thriving colonies, or self-sufficient space habitats rarely confront the full scope of Earth's role in sustaining life. The reality is far grimmer. We are not self-sufficient. We are a species intricately enmeshed in a planetary web that cannot be fully replicated elsewhere. Our survival depends not just on machinery or ingenuity, but on the complex, interwoven systems of our home planet. The more we consider leaving Earth, the clearer it becomes that the planet itself is irreplaceable. Every breath, every drop of water, every bite of food is a reminder that we are tethered to a world that, unlike spacecraft or artificial habitats, can sustain life without constant intervention. No rocket, no dome, no life support system can fully substitute for the richness and resilience of Earth's ecosystems. In short, even if we can launch ourselves into space, our survival remains profoundly and unavoidably earthbound. Even if we could overcome the physical and biological challenges of space travel, the fragility of our bodies, the ravages of radiation, the isolation, and our dependence on Earth's resources,
There remains another obstacle that is often overlooked: the staggering economic cost. Space is not merely inhospitable, it is extraordinarily expensive. Every launch, every spacecraft, every mission beyond low Earth orbit represents an investment of billions of dollars, resources that must be constantly replenished, and risk that can result in total failure. The dream of colonizing another world or establishing permanent habitats is not just a technical challenge. It is an economic one on a scale that dwarfs nearly every human endeavor. Consider the International Space Station, humanity's most ambitious and sustained space project. Built over decades, it required over $150 billion in construction and support costs, with thousands of engineers, scientists, and astronauts involved. Even then, the ISS supports only a handful of people at a time, with no capacity for self-sufficiency. Every meal, every drop of water, every kilogram of oxygen must be sent from Earth or recycled with painstaking effort. The station's continued operation requires regular resupply missions, each costing hundreds of millions of dollars. In other words, even for short-term habitation, the economic burden is astronomical. Now imagine taking that to the next level: establishing a permanent colony on Mars. Estimates for such a project, even in the most optimistic projections, range from hundreds of billions to trillions of dollars. And unlike the ISS, a Martian colony would face extreme isolation, environmental hazards, and resource scarcity. Every habitat module, every life support system, every energy source must be transported across hundreds of millions of kilometers of space. Even the most carefully planned missions would be economically unsustainable without continuous support from Earth. The cost of transporting supplies alone would be prohibitive, and any mission failure could mean the loss of billions of dollars and lives simultaneously.
Private companies like SpaceX have promised to make interplanetary travel more economically feasible, but the scale of investment required remains staggering. Rockets, fuel, infrastructure, and human support systems must be built to survive in environments that are utterly alien. Unlike terrestrial projects, there is no local economy to absorb costs or provide raw materials. Every resource must either be carried from Earth or generated on-site with technology that is still largely experimental. That means each step toward colonization carries not only financial risk, but existential risk as well. A single miscalculation could bankrupt entire programs and leave people stranded in hostile environments. Even if we accept such costs as possible, there is another layer: sustainability. Sending humans to another planet is one thing. Keeping them alive permanently is another. Short-term missions can be managed with resupply from Earth, but permanent settlements would require self-sufficiency in food, water, energy, and shelter. Every aspect of this self-sufficiency comes with enormous upfront investment in research, technology, and infrastructure. Terraforming, the fantasy of turning another planet into a livable world, would require orders of magnitude more resources, spanning centuries or even millennia, at costs beyond comprehension. In short, the economic demands of leaving Earth are not linear. They escalate exponentially the further we attempt to go. The economic reality also highlights an uncomfortable truth. Space colonization is likely to be accessible only to the ultra-wealthy or state-sponsored projects. For the average human, the cost of even traveling to another planet is effectively prohibitive. The billions required for one mission could instead fund global initiatives to sustain life on Earth, mitigate climate change, or eradicate poverty. And yet, as a species, we often prioritize exploration and expansion over maintaining the only home we can survive on. The paradox is striking. We dream of leaving Earth, while the price of doing so reminds us that we are still utterly dependent on it. Furthermore, the costs are not just financial. They ripple into energy and societal priorities. Every dollar, ton of fuel, and hour of human effort must be justified in the face of limited resources. Decisions about interplanetary missions force trade-offs. Advanced healthcare, infrastructure, environmental protection, or education on Earth might be sacrificed to fund endeavors in space that serve ambition more than necessity.
The economic barrier is a mirror of our technological and biological limitations, showing that even if we could survive the journey, the act of leaving Earth may remain beyond our collective means. Ultimately, the economic argument reinforces the stark reality. Leaving Earth is not simply a matter of willpower, ingenuity, or courage. It is a commitment of unprecedented scale, one that strains every resource and challenges the priorities of civilization. Billions of dollars spent on a single mission would barely support a handful of humans in a hostile environment for a few months. The dream of permanent colonization, of creating a second Earth, is therefore not just physically and biologically difficult, it is economically almost inconceivable. The numbers alone act as a tether, binding humanity to the very planet we dream of leaving, and forcing us to recognize that our ambitions must contend not only with the universe, but with the reality of scarcity and cost. Mars has always been the emblem of humanity's interplanetary dreams. Red, barren, and hauntingly beautiful, it represents both the ultimate challenge and the most achievable next step in our quest to leave Earth. Yet for all its appeal, Mars is a cruel teacher, revealing the limits of our technology, biology, and ambition. Decades of research, simulations, and robotic missions have taught us one sobering truth. We cannot safely live there for more than a few months. The planet is not merely inhospitable, it is a gauntlet of extremes that punish the slightest miscalculation. Mars's atmosphere, often romanticized as thin, is almost laughably insufficient to support human life. Composed primarily of carbon dioxide with less than 1% oxygen, it cannot sustain respiration. The surface pressure is less than 1% of Earth, so any tiny leak in a suit or habitat can have catastrophic consequences. Without continuous life support, humans would suffocate or experience rapid decompression in minutes. Unlike Earth, there is no magnetic field to deflect solar radiation or cosmic rays. The planet's surface is constantly exposed to ionizing radiation that would devastate human DNA over time, and dust storms that can envelop the entire planet for months create hazards both mechanical and biological, infiltrating habitats and machinery. Temperature adds another layer of hostility. Average surface temperatures hover around -60 degrees Celsius, with nighttime lows plunging to -125 degrees Celsius near the poles. Even the equator, often portrayed as the most hospitable region, experiences swings that would freeze unprotected humans within minutes. Energy management on Mars is therefore not just a convenience, it is a life-or-death necessity. Habitats must maintain internal temperatures near 20 degrees Celsius while shielding occupants from radiation and conserving precious energy for air, water, and communications. Every single system is a potential point of failure, and redundancy, while essential, dramatically increases the complexity and cost of any mission. Water scarcity complicates survival further. While ice exists beneath the Martian surface and water vapor floats in the thin atmosphere, extracting it is technologically challenging and energy intensive. Life cannot survive without consistent access to liquid water, and the processes to obtain it, melting ice, extracting it from soil, or chemically producing it, are slow and fraught with risk. A breakdown in water production could leave astronauts vulnerable to dehydration or force a return to Earth long before any permanent settlement becomes feasible. Food production presents yet another hurdle. Crops grown in Martian soil must contend with extreme cold, low atmospheric pressure, and a lack of essential nutrients. Hydroponics or aeroponics systems offer a theoretical solution, but they require massive energy inputs and constant monitoring. Even with controlled environments, yields are limited, and failures could jeopardize the entire mission. The logistics of sending enough food from Earth to sustain a crew for months, let alone years, are staggering, highlighting how dependent any Martian colony would be on resupply missions, a fragile lifeline stretched across hundreds of millions of kilometers. Psychological factors on Mars are equally severe. Isolation is absolute, communication with Earth delayed by 4 to 24 minutes each way, depending on orbital positions. The barren landscape, lacking familiar earthly cues, offers no comfort or sense of connection. Crews would live in confined habitats, performing repetitive tasks while facing constant awareness that rescue is not only improbable, but could take months or years. Even seasoned astronauts experience stress, sleep disturbances, and interpersonal strain in the relative safety of low Earth orbit. Mars multiplies these pressures 100-fold. All of these factors converge to limit the duration humans can realistically survive on Mars. Simulations like the Mars Desert Research Station and the HIC's project in Hawaii provide insight. Yet even in these controlled analog environments, crews struggle with isolation, resource management, and psychological stress. Remove Earth entirely from the equation, and the situation becomes exponentially more dangerous. Current technology allows for a stay of several months, perhaps up to a year with careful planning, but permanent habitation is a goal that remains firmly in the realm of theory. Even if a colony were technologically possible, it would be a fragile one. Every habitat, every energy system, every life support module will require continuous maintenance, constant monitoring, and an almost obsessive attention to redundancy. A single failure, a pump breaking, a solar panel malfunctioning, a leak in the oxygen generator, could have immediate and irreversible consequences. Mars is unforgiving, and even the smallest oversight could doom an entire crew. Mars illustrates a critical truth about space colonization. Proximity does not equal habitability. It is our closest planetary neighbor, yet it remains far more alien and hostile than most of us can intuitively grasp. For decades, humanity has dreamed of planting flags, building cities, and expanding our civilization to the red planet. But the reality is stark. The planet itself imposes a harsh limit, making long-term survival extraordinarily difficult, expensive, and dangerous. Mars is a test case not of ambition, but of our limits, a reminder that leaving Earth permanently is far more complicated than reaching another world. In the end, Mars is both a beacon and a warning. It represents what we can aspire to reach, but also underscores the fragility and constraints of human life outside Earth. Even with decades of preparation, technological innovation, and careful planning, the reality is that we cannot yet safely sustain life there for more than a few months, and the dream of turning it into a second home remains far beyond our current capabilities. Mars teaches us humility, that while the cosmos invites our curiosity, it also enforces its indifference, demanding respect for limits we may never fully overcome. Even beyond the challenges of life on planetary surfaces like Mars, the act of traveling through space itself is fraught with dangers that are both constant and invisible. Space is not simply empty. It is a high-speed gauntlet where even the tiniest particles can become lethal weapons. Micrometeoroids, for instance, are fragments of rock or metal traveling at velocities of tens of kilometers per second. To put that in perspective, that is faster than a bullet multiplied hundreds of times over. A particle the size of a grain of sand striking a spacecraft at such speeds can punch through metal, rupture life support systems, or send lethal debris flying inside the cabin. Shields can protect against many of these impacts, but no material is perfect. The universe provides no warning, no margin for error. One unexpected collision could spell disaster for a crew of astronauts thousands or even millions of kilometers from rescue. Equipment failure is another ever-present threat. Spacecraft are marvels of engineering, but even the most advanced systems are vulnerable to wear, manufacturing defects, or the harsh environment of space. Pumps, valves, air filters, and power systems must all function perfectly, often for years without interruption. A single malfunction can have catastrophic consequences. On Earth, a critical failure is inconvenient. In space, it is often fatal. Systems that regulate air pressure, temperature, and oxygen levels are intricate, interdependent, and delicate. Even a seemingly minor issue, a clogged filter, a misaligned solar panel, or a cracked circuit can quickly escalate into a life-threatening emergency. Unlike terrestrial engineering, where repairs are immediate and spare parts abundant, astronauts in deep space face the challenge of repairing critical systems with limited tools, materials, and support, sometimes hundreds of millions of kilometers away from Earth. The vacuum of space itself is perhaps the most absolute danger. Unlike Earth, space offers no air to breathe, no atmospheric pressure to hold our bodies together, and no warmth to moderate temperature extremes. Human biology is finely tuned to Earth's conditions. Remove those conditions and survival becomes nearly impossible. Without a pressurized suit, a human exposed to the vacuum would suffer rapid decompression, boiling of bodily fluids, and oxygen deprivation within seconds. Temperatures swing from hundreds of degrees below zero in shadowed regions to hundreds of degrees above zero under direct sunlight, creating a thermal environment incompatible with organic life. Radiation, already discussed as a constant threat, adds another layer of fatal risk, compounding the impossibility of unprotected survival. Even during routine missions within the relative safe confines of low Earth orbit, astronauts rely on redundancies and constant monitoring to stay alive. Multiply that risk by the duration, distance, and isolation of interplanetary or interstellar travel, and the odds become staggering. There is no natural refuge, no backup system that can spontaneously appear. Survival depends entirely on the integrity of human engineering and the vigilance of the crew. Long-term survival in space is not merely difficult, it is an extreme gamble against an environment that is hostile at every level, from subatomic particles to the vacuum itself.
Cosmic travel also magnifies the consequences of human error. Every maneuver, every repair, every calculation carries life or death stakes. Docking a spacecraft, navigating between planets, or correcting orbital trajectories might seem routine with computers and training, but in the vacuum of space, mistakes are irreversible. A single misstep can strand a mission in the void, leave a crew adrift, or destroy critical equipment. Unlike the oceans, deserts, or mountains of Earth where humans can survive long enough for rescue or adaptation, the vacuum of space offers no second chances. The combination of micrometeoroids, equipment fragility, and the lethal environment of the vacuum creates a reality starkly different from the romanticized visions of starship travel. Science fiction often portrays interstellar voyages as epic adventures, but the truth is far harsher. Every moment in space requires vigilance. Every system must be maintained. Every particle of debris avoided or mitigated. The margin between life and death is razor thin, and the scale of risk increases exponentially with distance from Earth. Even with advances in shielding, robotics, and artificial intelligence, the fundamental dangers of space remain. No technology can eliminate micrometeoroid strikes entirely, prevent every equipment failure, or alter the immutable properties of vacuum. Humans are, quite literally, passengers on a journey where the universe shows no mercy. Each mission into deep space is a confrontation with extreme physics, with consequences immediate and irreversible. This is why the dream of interstellar colonization is so difficult to reconcile with reality. We can send probes, rovers, and robots, devices built to withstand environments that humans cannot endure, but human bodies, fragile and dependent on Earth, cannot survive the vacuum for long without constant protection. Every step further from our home planet increases risk and reduces redundancy. The farther we go, the thinner the safety net, until eventually survival becomes a near impossibility. In the end, the dangers of cosmic travel reveal a profound truth. Space is not simply a frontier to be explored, but a fundamentally hostile environment in which human life is precarious, fleeting, and constantly at risk. Micrometeoroids, equipment failure, and the vacuum itself serve as reminders that despite our ingenuity and courage, the universe is not designed for us. It enforces limits that cannot be negotiated, offering neither compromise nor second chances, and in doing so reinforces the extraordinary rarity and fragility of life on Earth. Every human cell, every tissue, every organ in our body is a product of billions of years of evolution under very specific conditions that exist only on Earth. From the moment life first emerged, organisms have adapted to the pull of gravity, the composition of our atmosphere, the protection of the magnetic field, and the intricate web of biogeochemical cycles that sustain life. Our biology is not general purpose. It is finely tuned to a narrow range of environmental parameters. Remove those parameters and the complex systems that sustain life begin to fail, often in ways that are slow, invisible, and cumulative. Gravity, for example, is something we take for granted, yet it plays a critical role at every scale of our physiology. Our bones are dense and strong because they bear weight. Our muscles are built for movement against resistance. Fluids circulate under the influence of a constant downward pull. Even our inner ear's balance system relies on the force of gravity to orient us. In microgravity or low-gravity environments, these systems begin to break down. Bones lose mineral density at alarming rates, muscles atrophy despite rigorous exercise, and the heart struggles to maintain efficient blood flow. Beyond the physical, gravity also affects cellular processes. Studies have shown that microgravity can alter gene expression, affect cell division, and disrupt signaling pathways, potentially impairing immune function and healing. Our dependence on Earth goes deeper than gravity. Every cell operates in a chemical and thermal environment that is constant on this planet. Temperature, atmospheric composition, pressure, and even geomagnetic forces influence cellular processes. Our metabolism, enzyme function, and cellular repair mechanisms all assume these constants. Remove them and homeostasis, the delicate balance that keeps life stable, begins to unravel. Even subtle deviations can have cascading effects. Over weeks and months, organs weaken, immune responses falter, and physiological systems no longer function optimally. Earth's biosphere also provides countless invisible supports that our cells depend on. Oxygen is generated through photosynthesis, carbon dioxide is cycled naturally, and water is purified through a continuous planetary system. Microbes in soil, oceans, and the human microbiome interact to sustain life in ways that are interdependent and finally balanced. Outside this network, the environment becomes artificial, fragile, and prone to failure. Every life support system we engineer must attempt to replicate billions of years of evolution in miniature, a task of staggering complexity. Fail even slightly, and the consequences for human biology are immediate.
Even on the scale of a single cell, Earth's conditions matter. Radiation levels on Earth are low and relatively stable because of the atmosphere and magnetic field. Beyond it, cosmic rays and solar radiation bombard DNA, proteins, and membranes, initiating damage that cells struggle to repair. Microgravity further complicates repair mechanisms, making cellular breakdown a gradual but inevitable process over time. Life outside Earth is possible only because of extraordinary artificial protection. Remove that, even temporarily, and humans begin to degrade. The biological dependence of humans on Earth is not merely inconvenient, it is absolute. We are not modular organisms that can adapt instantly to alien environments. Every system, from the molecular to the organ level, is optimized for a single planet. This dependence explains why astronauts returning from months in space require extensive rehabilitation, why long-term low-gravity habitats present profound health risks, and why colonizing other worlds is not merely a matter of engineering shelters or supplying resources. Our very biology resists it. Ultimately, this dependence highlights the uniqueness of our home. Earth is not interchangeable with any other environment. It is the context in which life evolved and continues to thrive. Without it, our bodies, which seem so robust, begin a slow and inevitable breakdown. Every breath, every heartbeat, every cell is a reminder that we are inextricably tied to our planet. Biological dependence is not just a limitation, it is a tether, binding humanity to the delicate, intricate, and life-sustaining systems of Earth. To leave is to confront forces that our evolution never prepared us to face, and to attempt permanence elsewhere is to fight a battle against the very foundation of our biology. The idea of terraforming, transforming a hostile planet into a second Earth, is one of the most seductive fantasies of space exploration. Science fiction has given us images of verdant Martian landscapes, Earth-like skies on Venus, or oceans and forests blossoming on distant exoplanets. But in reality, terraforming is far from the realm of engineering tricks or clever architecture. It is a staggering biological, chemical, and physical problem, one that humanity is nowhere near solving.
It is not simply a matter of erecting domes, pumping in oxygen, or planting a few hardy crops. To create a truly habitable environment, one that could sustain human life for generations, we would have to rebuild an entire biosphere from scratch, and that task is orders of magnitude more complex than anything humans have ever attempted. A biosphere is not just air, water, and soil. It is an intricate web of interactions among countless species, chemical cycles, and geological processes. On Earth, the balance of oxygen, nitrogen, and carbon dioxide is maintained by forests, oceans, microorganisms, and even volcanic activity. Water cycles, nutrient flows, and soil fertility operate in concert with life itself. Reproducing these systems artificially on another planet would require a complete understanding of ecology, biology, and chemistry, knowledge that we do not currently possess even on our home planet. Small mistakes could have catastrophic consequences. Introduce the wrong microbial population and an ecosystem could collapse. Miscalculate atmospheric composition and oxygen levels could fluctuate dangerously, fail to maintain soil chemistry, and plants could fail to grow entirely. Take Mars as an example. Its atmosphere is thin, composed of over 95% carbon dioxide with less than 1% oxygen. Its surface is bombarded by radiation, and temperatures fluctuate dramatically, often plummeting hundreds of degrees below freezing at night. Simply adding oxygen to the air is not sufficient. The planet lacks pressure to retain it, lacks magnetic shielding to prevent radiation from destroying life, and lacks liquid water in usable quantities across the surface. To terraform Mars, we would need to create a stable atmosphere, generate a magnetosphere or alternate radiation protection, introduce liquid water, regulate temperatures, and establish sustainable ecosystems capable of recycling air, water, and nutrients indefinitely. Each of these tasks alone is a monumental challenge. Together, they form a problem so complex it exceeds not just our current technology, but perhaps the limits of human civilization itself. Even if we ignore the technical impossibilities, the time scales are staggering. Estimates for Mars range from centuries to millennia for partial terraforming, and full ecological stability would likely take far longer. We are not talking about decades or even a single human lifetime. To transform an entire planet would require sustained effort across countless generations, with meticulous management and continuous adaptation to unpredictable outcomes. Unlike a laboratory or a small habitat on Earth, a planetary-scale ecosystem is not isolated. Feedback loops, tipping points, and chaotic interactions make prediction and control nearly impossible. The slightest imbalance could derail centuries of work, leaving a hostile environment unchanged or worse, irreversibly altered in ways that make survival even harder.
The fantasy of domes or enclosed habitats often overshadows these realities. While building a pressurized, radiation-shielded dome is technologically feasible, it does not equate to creating a planet. Life inside a dome is dependent on constant maintenance, energy, and resupply. It is not self-sustaining, nor is it resilient to failure. One leak, one mechanical breakdown, or one lapse in resource management could be catastrophic. Domes are stopgap solutions, temporary islands of habitability, not independent, thriving planets. There is also the question of energy. Terraforming a planet would require unprecedented amounts of energy to alter the atmosphere, melt polar ice, generate heat, and maintain ecological balance. We do not possess the means to generate, store, or deploy energy on the planetary scale necessary for such transformations. Any attempt at large-scale planetary engineering would likely consume resources on an almost unimaginable scale, rivaling or exceeding the total energy and material consumption of humanity on Earth. Terraforming, in short, is less a technological challenge than a conceptual one. It forces us to confront the limits of human control over nature. Earth is not simply a backdrop for life. It is a finely tuned system that sustains life in ways we barely understand. Attempting to recreate such a system elsewhere, under harsher and less forgiving conditions, is not a question of ambition, but of feasibility. Even with all our ingenuity, decades of planning, and technological advancement, the prospect of a second Earth remains a near impossible dream, a reminder of how singular and extraordinary our planet truly is. Ultimately, the illusion of terraforming reveals a deeper truth. No dome, no engineered atmosphere, no artificially sustained ecosystem can replicate the richness, resilience, and stability of Earth. The fantasy of turning another world green is seductive, but it obscures the fact that life depends on complexity and interconnection at a planetary scale, systems we cannot hope to rebuild elsewhere. In chasing the dream of a second Earth, we are forced to confront the reality that Earth itself is irreplaceable, and the survival of humanity may depend not on leaving, but on protecting and understanding the only biosphere we truly belong to. Even if we could solve the biological, psychological, and ecological challenges of space colonization, there remains a problem that is inescapable and absolute: energy. The universe operates on scales of power and force that make even our most ambitious human endeavors appear puny. Traveling through space, constructing colonies, and sustaining life outside Earth are not just difficult, they are extraordinarily energy-intensive tasks in ways that dwarf our current technological capacity. To leave Earth and survive elsewhere, we would need to harness, store, and manage energy at levels that verge on the staggering, and the implications of this reality are sobering. Consider first the energy required simply to escape Earth's gravity. Launching a spacecraft is an exercise in overcoming an immense natural barrier. Earth's gravity binds everything to its surface, from the tiniest pebble to the largest ship. To escape that pull, rockets must reach a velocity of approximately 11 kilometers per second, a speed that requires vast amounts of fuel, precise engineering, and immense energy expenditure. Even small payloads demand enormous amounts of propellant, and every additional kilogram sent into orbit multiplies energy requirements exponentially. This is why sending humans beyond low Earth orbit, let alone to Mars or beyond, is vastly more complex and expensive than launching satellites or robotic probes. Energy in this sense is not simply fuel. It is the fundamental currency of space exploration, one we spend lavishly for even the briefest journeys. But travel is only the beginning. Sustaining colonies on other worlds is an energy problem on an entirely different scale. Life support systems, designed to replicate Earth's atmosphere, pressure, and temperature, require continuous power. Oxygen must be produced or recycled, water must be purified and conserved, habitats must be heated in extreme cold or cooled under harsh sunlight, and waste must be processed to maintain health and hygiene. Every aspect of daily life, from cooking to lighting to communication with Earth, demands energy. On Earth, these systems are powered effortlessly by established infrastructure and abundant natural resources. In space or on Mars, energy is a precious commodity, limited by solar exposure, fuel capacity, and technological efficiency. Every watt must be carefully accounted for, and failure to supply even a small amount can have cascading consequences for human survival. Building infrastructure beyond Earth amplifies this demand further. To construct habitats, laboratories, greenhouses, and protective shields, enormous amounts of material must be transported, processed, or manufactured on site, each step requiring energy. Unlike Earth, where raw materials are readily available, extraterrestrial environments often require importing mass from the planet's surface, refining local resources under extreme conditions, or converting raw elements through energy-intensive chemical processes. Terraforming or large-scale engineering, even if theoretically possible, would require energy on a planetary scale. Estimates suggest that altering Mars's atmosphere, melting its polar ice to generate liquid water, or increasing surface pressure to Earth-like levels would demand energy comparable to centuries of global consumption on our home planet. The numbers are simply beyond human experience. Even communication across vast distances consumes energy. Maintaining contact with distant colonies or probes requires powerful transmitters and precise instruments. Data relayed over hundreds of millions of kilometers cannot rely on casual transmission. Signals must be amplified, repeated, and corrected, all consuming finite resources. Energy in this sense is not only a matter of propulsion or survival, but also of maintaining human connection across the void, a necessary condition for any functional off-world society.
The energy problem also highlights the limits of current technology. Solar panels, the most viable source for space-based colonies, are limited by efficiency and availability of sunlight, particularly on distant or partially shaded planets. Nuclear power offers longevity, but introduces safety risks, waste management issues, and technical complexity. Chemical fuels, while powerful, are heavy, finite, and difficult to transport in the quantities required for long-term settlement. In short, we do not yet have an energy system capable of supporting sustained human life beyond Earth, and every proposed solution carries trade-offs, risks, and monumental costs. The cumulative energy demands for space colonization reveal an uncomfortable truth. Leaving Earth is not just a technological or biological challenge, it is a problem of resource economics on a cosmic scale. The energy required to lift humans into space, protect them, feed them, shelter them, and maintain infrastructure is almost incomprehensible. Each additional colonist, each additional habitat, each extension of survival multiplies the energy needed, quickly exceeding our current and near-future capabilities. It is not merely difficult, it is a challenge that scales exponentially with ambition. Even with breakthroughs in fusion power, advanced solar technologies, or new propulsion methods, the fundamental principle remains: energy is the currency of survival in space, and the amounts required to build sustainable colonies are extraordinary. Earth provides an energy-rich environment naturally, through sunlight, fossil fuels, chemical cycles, and geothermal forces. Beyond Earth, there is no safety net, no convenient source. Energy must be generated, managed, and conserved with precision, or life will falter. Ultimately, the energy problem reinforces a central theme of humanity's cosmic limitations. We may dream of distant worlds, of interstellar travel and permanent colonies, but the universe does not operate on ambition alone. It demands power in quantities that challenge our imagination for every single step we take away from Earth. Even if technology, biology, and resources were perfected, the energy required to sustain such endeavors might alone tether us to our home planet, reminding us that survival in space is not simply about will or courage, but about the fundamental physics of the cosmos. Beyond the physical, biological, and logistical challenges of leaving Earth lies a dimension often overlooked but profoundly powerful: our emotional and psychological bond with our planet. Earth is not just a location where life happens, it is intertwined with the very fabric of our identity, consciousness, and sense of belonging. Every human being has evolved in an environment defined by gravity, atmosphere, cycles of day and night, seasonal rhythms, and a mosaic of ecosystems. These constants shape not only our biology, but also our perceptions, emotions, and the way we relate to the world. To leave Earth forever is to sever a connection that is fundamental to what it means to be human, and doing so may be psychologically unbearable. The bond begins at the most intimate level. Humans instinctively seek natural landscapes, respond to the sound of water, feel comfort in sunlight, and experience relaxation in the shade of trees. Evolution has wired us to read cues from our environment: the changing seasons, the arc of the sun, the cycle of tides, the smell of soil after rain. These environmental signals anchor our mental health, regulate circadian rhythms, and even influence emotional well-being. In space or on alien worlds, these cues vanish. Artificial lighting, sterile habitats, and barren landscapes cannot replicate the richness of Earth's sensory environment. The deprivation of these familiar signals slowly erodes mental stability, creating stress, anxiety, and a sense of disconnection from the natural world we are biologically tuned to inhabit. Beyond sensory input, there is the profound emotional attachment to the concept of home. Earth is more than a physical location. It is a repository of memory, culture, and shared human experience. Even astronauts, who have trained for years to live in space, often describe the view of Earth from orbit as emotionally overwhelming. A small, fragile, blue and green sphere suspended in darkness, home to every person, every ecosystem, every story. This emotional resonance is not superficial, it is deeply ingrained. The planet's landscapes, skies, oceans, and weather patterns have shaped human imagination, art, mythology, and identity for millennia. To leave Earth permanently is to leave behind not only resources and protection, but also the intangible qualities that sustain our sense of self. The psychological burden of permanent separation would be severe. Humans are social and culturally grounded, but we are also geophysically grounded. We are creatures whose cognition, emotion, and perception have co-evolved with a planet's gravity, atmospheric pressure, and environmental rhythms. Alien environments, whether the barren plains of Mars, the icy moons of Jupiter, or the vacuum of deep space, are not merely inhospitable. They are alien to the very framework through which humans experience the world. Lifelong exposure to such conditions could induce chronic stress, depression, disorientation, and even existential despair. The mind, like the body, is Earth-dependent, and removing that dependence could have consequences as profound as those caused by microgravity or radiation.
The energy problem also highlights the limits of current technology. Solar panels, the most viable source for space-based colonies, are limited by efficiency and availability of sunlight, particularly on distant or partially shaded planets. Nuclear power offers longevity, but introduces safety risks, waste management issues, and technical complexity. Chemical fuels, while powerful, are heavy, finite, and difficult to transport in the quantities required for long-term settlement. In short, we do not yet have an energy system capable of supporting sustained human life beyond Earth, and every proposed solution carries trade-offs, risks, and monumental costs. The cumulative energy demands for space colonization reveal an uncomfortable truth. Leaving Earth is not just a technological or biological challenge, it is a problem of resource economics on a cosmic scale. The energy required to lift humans into space, protect them, feed them, shelter them, and maintain infrastructure is almost incomprehensible. Each additional colonist, each additional habitat, each extension of survival multiplies the energy needed, quickly exceeding our current and near-future capabilities. It is not merely difficult, it is a challenge that scales exponentially with ambition. Even with breakthroughs in fusion power, advanced solar technologies, or new propulsion methods, the fundamental principle remains: energy is the currency of survival in space, and the amounts required to build sustainable colonies are extraordinary. Earth provides an energy-rich environment naturally, through sunlight, fossil fuels, chemical cycles, and geothermal forces. Beyond Earth, there is no safety net, no convenient source. Energy must be generated, managed, and conserved with precision, or life will falter. Ultimately, the energy problem reinforces a central theme of humanity's cosmic limitations. We may dream of distant worlds, of interstellar travel and permanent colonies, but the universe does not operate on ambition alone. It demands power in quantities that challenge our imagination for every single step we take away from Earth. Even if technology, biology, and resources were perfected, the energy required to sustain such endeavors might alone tether us to our home planet, reminding us that survival in space is not simply about will or courage, but about the fundamental physics of the cosmos. Beyond the physical, biological, and logistical challenges of leaving Earth lies a dimension often overlooked but profoundly powerful: our emotional and psychological bond with our planet. Earth is not just a location where life happens, it is intertwined with the very fabric of our identity, consciousness, and sense of belonging. Every human being has evolved in an environment defined by gravity, atmosphere, cycles of day and night, seasonal rhythms, and a mosaic of ecosystems. These constants shape not only our biology, but also our perceptions, emotions, and the way we relate to the world.
To leave Earth forever is to sever a connection that is fundamental to what it means to be human, and doing so may be psychologically unbearable. The bond begins at the most intimate level. Humans instinctively seek natural landscapes, respond to the sound of water, feel comfort in sunlight, and experience relaxation in the shade of trees. Evolution has wired us to read cues from our environment: the changing seasons, the arc of the sun, the cycle of tides, the smell of soil after rain. These environmental signals anchor our mental health, regulate circadian rhythms, and even influence emotional well-being. In space or on alien worlds, these cues vanish. Artificial lighting, sterile habitats, and barren landscapes cannot replicate the richness of Earth's sensory environment. The deprivation of these familiar signals slowly erodes mental stability, creating stress, anxiety, and a sense of disconnection from the natural world we are biologically tuned to inhabit. Beyond sensory input, there is the profound emotional attachment to the concept of home. Earth is more than a physical location. It is a repository of memory, culture, and shared human experience. Even astronauts, who have trained for years to live in space, often describe the view of Earth from orbit as emotionally overwhelming. A small, fragile, blue and green sphere suspended in darkness, home to every person, every ecosystem, every story. This emotional resonance is not superficial, it is deeply ingrained. The planet's landscapes, skies, oceans, and weather patterns have shaped human imagination, art, mythology, and identity for millennia. To leave Earth permanently is to leave behind not only resources and protection, but also the intangible qualities that sustain our sense of self. The psychological burden of permanent separation would be severe. Humans are social and culturally grounded, but we are also geophysically grounded. We are creatures whose cognition, emotion, and perception have co-evolved with a planet's gravity, atmospheric pressure, and environmental rhythms. Alien environments, whether the barren plains of Mars, the icy moons of Jupiter, or the vacuum of deep space, are not merely inhospitable. They are alien to the very framework through which humans experience the world. Lifelong exposure to such conditions could induce chronic stress, depression, disorientation, and even existential despair. The mind, like the body, is Earth-dependent, and removing that dependence could have consequences as profound as those caused by microgravity or radiation.
Furthermore, leaving Earth forever carries the weight of isolation from life itself. On any other world, we would be separated from the biosphere that has nurtured our species. The forests, oceans, skies, and microbial life that collectively sustain and inspire us. Our very sense of belonging is tied to this living network. Beyond Earth, humans are no longer part of this ecological community, but intruders in a hostile void. The psychological strain of knowing that we are cut off from every familiar form of life, every natural cycle, and every shared human history is difficult to overstate. The emotional bond to Earth also underpins our sense of purpose. Our identities are not abstract. They are shaped by the planet that hosts them. The sky, mountains, rivers, deserts, and oceans inform our stories, art, science, and spirituality. To sever that connection is not just to move physically, but to displace the mind itself from the context in which it evolved. While technological simulations, artificial windows, greenhouses, Earth-like habitats may mitigate some effects, they are pale shadows of the dynamic, interconnected world that has sustained humanity for eons. Even those who dream most passionately of space exploration must confront this truth. Leaving Earth is not a simple relocation. It is an uprooting of human experience itself. Our physiological and psychological systems are intertwined with the planet's rhythms and systems. Without Earth, we risk losing not only our safety and sustenance, but also our identity, emotional stability, and connection to the living network of which we are a part. Ultimately, the emotional bond we share with Earth reinforces why leaving may be more than impractical.
it may be intolerable. No habitat, no spacecraft, and no artificial ecosystem can fully replace the psychological and emotional resonance of our home planet. Earth is embedded in our sense of self, our perception of life, and our understanding of what it means to exist. In contemplating interstellar travel or permanent colonization, we must remember that the cost is not only measured in resources or biology, but in the profound, irreplaceable connection that binds humans to their one true home. Beyond the tangible, physical, and psychological constraints of leaving Earth lies a deeper, often overlooked perspective, the philosophical dimension of our relationship with the planet. For centuries, humans have dreamed of escaping Earth, of reaching the stars, settling new worlds, and ensuring the continuity of our species elsewhere. These ambitions are noble in their imagination and daring in their execution. Yet perhaps the point of humanity's exploration is not merely to flee, but to understand, appreciate, and protect the world we already inhabit. In other words, our purpose may not be to abandon Earth, but to recognize its uniqueness, its fragility, and our responsibility toward it. Philosophically, the urge to leave often stems from a desire for survival, adventure, and expansion, traits deeply embedded in human nature. However, these traits can sometimes obscure a more fundamental truth. Earth is not merely a launching pad for exploration, it is the crucible in which life itself evolved. Every ecosystem, every species, and every geological process represents billions of years of planetary evolution. The very existence of humanity is a product of this environment, finely tuned and interdependent with countless other systems. To escape Earth without understanding it is to ignore the lessons embedded in the delicate balance that has sustained life. There is also a moral and ethical dimension. If the point of our species is to survive and flourish, then the wisest course may not be to scatter ourselves across the cosmos, but to ensure that the only place we can truly live remains habitable. Humanity has already demonstrated a profound capacity for destruction. Deforestation, pollution, climate change, and species extinction reveal the consequences of neglecting the systems that sustain life. Philosophically, our efforts might be better directed towards preserving and nurturing Earth rather than attempting to recreate it elsewhere. In this sense, exploration becomes not just an outward journey, but a reflective inward one, where understanding our planet and its intricacies becomes the ultimate adventure. Furthermore, leaving Earth as a species may not even solve the problems we hope to escape. No matter how technologically advanced we become, the cosmos imposes constraints that challenge human survival. The philosophical lesson embedded in this reality is one of humility. Perhaps our destiny is not to conquer other worlds, but to steward the one we have. The allure of space is undeniable, but it can obscure the profound value of Earth itself. Every desert, river, forest, and ocean contains wisdom about resilience, adaptation, and interconnection, knowledge that may be critical for sustaining humanity over the long term. The perspective that we are meant to protect rather than abandon our home also aligns with notions of responsibility and interconnectedness. Earth is not simply a resource to exploit, it is a system in which our lives are embedded. Water, air, soil, and climate are not interchangeable commodities, but components of an intricate network that sustain us. Philosophically, this challenges the common narrative of expansion and escape. True mastery of the cosmos may not lie in leaving, but in cultivating the intelligence, care, and foresight to safeguard the delicate systems that allow life to exist in the first place. Exploration in this context is reframed. It becomes an inward and outward journey, a way to study Earth from orbit, to understand its ecosystems, and to appreciate the fragility of the biosphere that sustains all life. Space missions, rather than being exercises in permanent relocation, may serve as instruments of reflection, education, and stewardship. Observing Earth from the vantage point of the stars reveals both its vulnerability and its beauty. This perspective, sometimes called the overview effect by astronauts, instills awe, humility, and a renewed sense of duty to protect our home rather than escape it. Philosophically, the cosmos itself may offer lessons of limits, resilience, and the impermanence of life.
While the universe is vast and largely indifferent to our existence, it is precisely this indifference that frames the importance of Earth. Our purpose in this light is not to flee the indifference of space, but to honor the rare and precious conditions that allow life to flourish here. In other words, the philosophical imperative is not interstellar conquest, but careful guardianship of our one habitable world. Ultimately, contemplating philosophical reasons for staying grounded challenges humanity to reframe its ambitions. The urge to leave Earth is powerful, but it may be guided by a misunderstanding of purpose. Perhaps true progress is not measured by how far we can go, but how well we can understand, protect, and sustain the world that gave us life. Space may offer inspiration and perspective, but Earth remains the irreplaceable foundation of our existence, deserving not only our admiration, but our vigilance. Protecting Earth may not be a retreat from ambition. It may be the most profound adventure of all, the one that ensures humanity has a home from which all other dreams can safely take flight.
The allure of space colonization often carries with it an implicit assumption that if Earth becomes inhospitable, humanity can simply move on to another world. This vision, however, exposes a profound environmental paradox. We dream of terraforming Mars, building self-sufficient colonies, or escaping to distant exoplanets, yet we struggle to sustain the one planet that already supports life, the only planet we truly belong to. The fantasies of space travel can, in fact, distract us from the urgent environmental challenges here on Earth. Climate change, deforestation, biodiversity loss, and pollution are not abstract threats. They are manifestations of humanity's inability to maintain the delicate systems that sustain life. The stark reality is this: we cannot escape our environmental responsibilities by looking outward, because the conditions that allow life to thrive elsewhere are far beyond our reach. Earth's environment is an intricate, self-regulating system shaped over billions of years. Atmosphere, oceans, soil, flora, and fauna interact in a complex web, cycling nutrients, stabilizing climate, and supporting ecosystems that include humans. Yet despite this perfection, human activity has disrupted these processes at unprecedented scales. Industrialization, overconsumption, and mismanagement have altered atmospheric composition, accelerated species extinction, and destabilized natural cycles that we often take for granted. To imagine leaving Earth while failing to maintain its biosphere is not just unrealistic, it is philosophically and practically contradictory. A planet like Mars or the Moon offers no safeguards, no ecosystems, no atmospheric balance. Attempting to start over elsewhere requires us to solve problems we have not yet mastered on our own world. There is also a moral dimension to this parallel. Space colonization is often framed as a backup plan, a way to preserve humanity in the event of disaster. Yet investing billions in spacecraft and interplanetary colonies while neglecting climate mitigation, reforestation, and conservation efforts on Earth is a form of escapism. It implies a belief that technology alone can compensate for environmental degradation, ignoring the complex, interdependent systems that make life possible. In truth, the solutions required to sustain human life in space, closed-loop ecosystems, artificial atmospheres, water recycling, energy management, mirror the same principles that are urgently needed on Earth: careful stewardship, efficiency, and respect for natural systems. Our failure to apply these lessons at home casts doubt on our ability to replicate them on another world. Moreover, the environmental parallel highlights a sobering limitation. Space colonization is not a practical safety net. No matter how advanced our technology, we cannot replicate Earth's ecosystems elsewhere with current capabilities. Every attempt to establish a new habitat would rely on Earth for supplies, knowledge, and energy for decades, if not centuries. The fantasy of leaving Earth to escape environmental collapse ignores the fact that without a functioning planet as a foundation, all other worlds remain uninhabitable. Colonization is not an insurance policy. It is a monumental and precarious engineering project. In contrast, the Earth we already inhabit is immediately habitable, resilient, and capable of sustaining billions of lives if we learn to respect and maintain it. This connection between environmental neglect and space ambitions also carries a cautionary psychological lesson. The desire to move on can reflect a human tendency to avoid confronting limits and responsibilities. Dreaming of other worlds offers hope, but it also risks fostering complacency about the fragility of our own. We cannot escape the consequences of mismanagement, overconsumption, or ecological collapse by imagining life elsewhere. Any hope of long-term survival, prosperity, or well-being remains tethered to the careful stewardship of Earth's biosphere. In a deeper sense, the environmental parallel underscores humility. Space is vast, empty, and indifferent, offering no guarantees, no support, and no inherent protection. Earth, by contrast, is extraordinary in its capacity to nurture and sustain life. Its ecosystems, biodiversity, and resources are unparalleled in the known universe. Ignoring that, in favor of fantasies of interplanetary escape, is both impractical and ethically troubling. The more we attempt to detach from our home planet, the more apparent it becomes that sustainability on Earth is not optional. Our ability to care for our planet is the true measure of our capacity to survive, whether here or anywhere else. Ultimately, the environmental parallel is a stark reminder. We cannot dream our way out of responsibility. Space colonization may inspire awe, curiosity, and ambition, but it cannot substitute for the work required to protect and sustain Earth. We can't truly move on if we can't even keep our own planet alive and thriving. Every ecosystem restored, every species preserved, every climate stabilized is a step toward the resilience and foresight that any human endeavor in space would demand. In that sense, our true journey may be learning to care for Earth, for it is the foundation of all human survival, the ultimate cradle that sustains life, and the one environment we are uniquely equipped to protect. There is a haunting yet profound notion that lingers beneath humanity's greatest cosmic ambitions, a concept that some call cosmic imprisonment. It suggests that perhaps we were never truly meant to leave Earth, that the universe, itself, vast and indifferent, has woven invisible boundaries around us, physical, biological, and existential, that keep us tethered to our cradle, not as a punishment, but as a condition of existence. From this perspective, the limits we face in our quest to explore the stars are not just technological challenges waiting to be solved, but fundamental laws of nature reminding us of our place within the grand order of the cosmos.
When we look at the universe, it's easy to be awestruck by its immensity. Billions of galaxies, each containing billions of stars, stretching across incomprehensible distances. Yet that immensity also defines the barriers that separate us. The distances between stars are not merely large, they are unbridgeable within the lifespan of human civilization as we currently know it. Even light, the fastest thing in the universe, takes years, centuries, millennia to traverse the vast gulf between suns. Our most advanced spacecraft, traveling at tens of thousands of kilometers per hour, would take tens of thousands of years just to reach the nearest star system. These are not arbitrary obstacles. They are cosmic walls of time and space that ensure life remains confined to its birthplace. Gravity, radiation, the vacuum of space, all are forces of nature that both define and restrain us. Earth's gravity holds us close, providing the essential conditions for life, but also binding us within its pull. Radiation beyond the planet's magnetic field bombards any traveler, threatening to unravel DNA and destroy cellular integrity. The vacuum beyond our atmosphere offers no air, no warmth, no sound, no comfort, only silence and death. Every attempt to venture beyond must contend with these immutable realities. It is as if the universe itself has set the terms of existence. Within your world, you may thrive, but beyond it, survival is an act of defiance. From a philosophical or even spiritual standpoint, this notion of cosmic imprisonment is both humbling and instructive. Perhaps the universe was never designed to be conquered by fragile creatures of flesh and bone. Maybe the laws of physics are not barriers to overcome, but boundaries meant to teach us reverence, to remind us that existence itself is miraculous, and that the rare oasis of life we call Earth is not something to escape, but something to cherish. The very hostility of the universe may be a lesson in perspective. The stars inspire us to dream, but they also teach us humility. We may gaze at them with longing, but they remind us how precious and improbable it is that we exist at all. There's also a deeper layer to this idea.
Perhaps confinement to Earth is necessary for our development. Every species evolves within constraints, and those constraints shape its behavior, intelligence, and survival. For humanity, being bound to a single planet might be what forces us to grow morally and intellectually, to learn stewardship, cooperation, and understanding before reaching outward. The universe, in this view, is not cruel, it is patient. It keeps us in our cradle until we prove we can care for it, until we learn not just to build and explore, but to preserve and respect. Even from a scientific standpoint, our imprisonment makes sense. Every part of our biology, from the cells in our muscles to the chemistry of our blood, is tuned to Earth's environment. Its gravity, its pressure, its magnetic field, its atmosphere. Remove us from these parameters and our bodies begin to break down. It is not just that space is hostile, it's that we are perfectly adapted to one specific home. That precision is not coincidence. It is evidence of deep evolutionary dependence. The conditions that sustain us exist nowhere else that we know of, and that in itself may be the universe's quiet way of saying, this is where you belong. But cosmic imprisonment doesn't have to be seen as limitation or defeat. It can be understood as a kind of protection. Within the confines of our planet, we have everything we need to live, learn, and evolve. We are not trapped, we are sheltered. The universe's vast distances and harsh realities ensure that we remain anchored to the only world capable of nurturing our growth. It may even be that the isolation of life on Earth serves a purpose, that until we learn to live in balance with our own planet, we have no right and no readiness to inhabit others. This interpretation reframes our struggle to reach the stars as part of a larger story about maturity. The cosmos, immense and silent, does not deny us out of cruelty, but offers us time to understand ourselves, time to learn the value of home. Our confinement may be the universe's way of ensuring we don't repeat our mistakes on a galactic scale. Before we can build other worlds, we must first learn not to destroy our own. In the end, the idea of cosmic imprisonment reminds us that the stars are not gates waiting to be opened, but mirrors reflecting our own limitations and responsibilities. We may never know if the universe has intention or design, but we do know this: it has given us Earth, a sanctuary of impossible beauty in a sea of emptiness. And perhaps, just perhaps, that is not a sentence, but a gift. After exploring the technological, biological, psychological, economic, and philosophical hurdles to leaving Earth and reflecting on the stark realities of space, it becomes clear that our planet is far more than a launching pad or a temporary home. Earth is not merely the backdrop of human life. It is a finely tuned, self-sustaining system that has nurtured life for billions of years. From the vast oceans that regulate climate and sustain food chains, to the atmosphere that shields us from lethal radiation, to the gravity that shapes our bodies and minds, Earth provides a constellation of conditions that make human existence possible. Every challenge we encounter when contemplating leaving, from radiation and microgravity to energy demands and isolation, serves as a mirror reflecting how extraordinary it is that life can thrive here at all.
In reflecting on this, there is a profound sense of awe. Earth is not a prison that confines us. It is a miracle that shelters, sustains, and inspires us. The vastness of the universe, the harshness of space, and the fragility of life beyond our atmosphere highlight a simple truth. We have been given something incredibly rare, perhaps unique, a habitable planet teeming with life. It is a cradle unlike any other, one that has allowed consciousness, culture, curiosity, and civilization to emerge. The fact that we can think, imagine, and dream about the stars is itself a testament to the extraordinary conditions provided by this small, spinning rock in the cosmic void. Dreams of escaping to other planets, while exciting and inspirational, may obscure the deeper, more essential journey: learning to stay, to nurture, and to understand our own world. Human ambition often drives us outward, seeking the unknown, but the challenges of space remind us that our survival, happiness, and growth are inseparable from Earth itself. Perhaps the truest form of exploration is not to conquer other planets,
but to explore the intricacies of our own biosphere, to uncover its mysteries, and to ensure that it remains vibrant and resilient for generations to come. Protecting forests, oceans, and biodiversity, mitigating climate change, valuing the delicate balance of ecosystems. These are the adventures that truly matter, the journeys that define our species in both courage and wisdom. This reflection invites a shift in perspective. Rather than viewing Earth as a starting point for escape, we might see it as the ultimate destination, a living, breathing masterpiece that demands our attention, care, and respect. Every sunrise, every rainstorm, every complex ecosystem is a reminder of what is rare, delicate, and irreplaceable. Instead of imagining life on Mars or distant exoplanets as a continuation of humanity, we should recognize that life on Earth is a continuation of life itself, and its preservation is the foundation for any future dreams, whether on this planet or beyond.
Ultimately, staying does not imply stagnation. On the contrary, it challenges us to channel our curiosity, ingenuity, and creativity toward understanding and preserving the only home we truly know. It is a journey of stewardship, empathy, and responsibility. A journey that is every bit as epic as interstellar travel, perhaps even more so because it is immediate, intimate, and essential. Earth gives us everything we need, but it also asks something in return: awareness, respect, and action. In the awe-inspiring scale of the cosmos, Earth may appear small, but in its capacity to sustain life, it is nothing short of miraculous. We are bound to it not by limitation, but by design, or by circumstance so perfect it feels intentional. The stars will always beckon, and human imagination will continue to reach outward. But the real adventure, the real journey, is here. It is in learning to stay, to live in harmony with our planet, to marvel at its wonder, and to safeguard the fragile miracle that is our home. Earth is not a prison. It is the most extraordinary gift the universe has given us, and perhaps the greatest exploration we will ever undertake is the one that keeps us grounded, attentive, and alive on this singular, remarkable world. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.